Wow, nice new red. Oh, it's black on your screen. Here it's red. Okay, well, I'm also very red on my screen. Okay, well, welcome. Good morning, afternoon, midday. This is EECS 240. First, do you have questions? Actually, you have at least one of them because I got it by email. Somebody very reasonably said, heck, look, I mean, what you're asking in problem 1, right? Homework problem 1, for those who haven't looked at it, is really design a one-transistor amplifier, a common source stage. So sort of lecture 1 of an undergraduate course. So it should be easy, right? You need to give us a little bit more data, that email said, in order to solve this problem. But, you know, the problem is that the fab, all it gives you is these bsim parameters that I've listed on the website. So where are the additional parameters coming from? Well, we got to figure that out, right? So I mean, at the risk that this is a little bit self-serving, my point that we need to look at device models from a special angle, namely from the angle of what are we going to do if we want to design circuits with these things, is a very solid one. Because what at least some of you've learned about models was very useful, and maybe you know a lot more about the physics of transistors than I do, but you can't design a single transistor amplifier, right? We want to fix that. So today we're going to fix this. Yes?
I was wondering, you said most of the time you want to avoid resistors if you can.
Yeah.
I was just wondering if anyone really uses resistors for like a relatively high gain stage or for a filter, or would they mostly use like a switch capacitor instead of a resistor?
Well, okay, so that's now a totally different topic, right? Where do we use filters? Well, where do you use resistors? And so references is one of the areas, right? Just constant or sort of supply independent currents or so. And the other thing is exactly filters is an important area where we use resistors. So there are these so-called switch capacitor filters that replace resistors with switches and capacitors. That works very well, and if you can do that, then most of the time that's the way to go. Now you can't do that if things go blazingly fast. A 1 gigahertz filter or so with switch capacitors, you know, probably not. 100 megahertz, hard, but maybe possible. Right? So the other thing is when we build so-called anti-aliasing filters, for example, then we need a continuous time filter, a filter that doesn't have switches, doesn't have a clock. And for that we really need resistors. Or we need simulations of resistors. A transconductor is kind of a resistor too, right? 1 over a resistor. So there are all sorts of ways to do that. So sometimes we'll use resistors, sometimes something else, sometimes switch capacitor filters, transconductors or whatnot, or MOSFETs to replace these resistors. At the end of the day, we need to know resistors, and we use them sometimes. And now, what sort of all these different cases are, or at least some of them, and how to deal with them, that's this other course, 247, that goes over those. So in 240, we really learn the plumbing. If we need that particular fitting, we know where it is. Okay. In 247, we'll figure out what are all the possible ways to do things, and then we can decide what part, what screw or nail or whatnot we want to use. So they kind of fit together, but is this enough on your question? All right. Other questions? Yeah.
Just one more question. I'm just curious, sort of what you're looking for in the answers to these problems. If you want to see hand calculations, and if so, you know, what types of hand calculations? It's obvious, like for problem. I mean, you can't solve these by hand, really.
Yes, you can. At the end of this class, or at least at maybe we'll lead a little bit into next class. You can solve this by hand, and you will be within 5–10% of SPICE. Believe it or not. Yeah, I will convince you. Yeah. So yeah.
I was just based on like the SPICE model being much more complicated.
Right. No, I mean obviously the way is not looking up all these crazy equations for the B-Sim 3 model and somehow trying to solve those. No. This is 2 or 3 lines. Then you're done. You have the answer. And it's a useful answer. Now, there are some tricks and so on, but well, it's not really tricks. It will be very, very simple and trivial, of course, but with hindsight, like all good science, once we understood it, heck, I mean, how could you ever do it differently? But right now, it may not be so obvious how we do that. Okay, so let's get started on this. I've said, of course, a lot of things about the square law model and its limitations in particular. That doesn't say that we should throw it out the door. It's still pretty much our best friend if we want to get a little bit of intuition about what's going on. And even though the actual values that come out of these equations are often fairly inaccurate, at least sort of the characteristics like regions of operation, saturation, weak inversion, and so on, that the square law model, or sort of the extended square law model, is good at telling us what those are, and we'll keep on using that nomenclature and so on, even though it doesn't map exactly on the device characteristics. Okay. Also, the square law model is actually accurate for devices that meet 2 constraints simultaneously. First of all, the channel length needs to be fairly large, a few micron or so. Okay. And the other thing is the oxide needs to be fairly thick. Also, the gate oxide needs to be fairly thick. And here we need an and. Both these conditions need to be fulfilled. So, for the EE240 technology, you, of course, can always fulfill, if you want, the first condition. You can always make a transistor with a very long channel, but you have no chance of getting that thick an oxide. The oxide thickness of our transistor, I believe, is 6.5 nanometers or so, a lot less than 50 nanometers. And then these devices just don't behave according to the square square law model. Really, what the reason here is that the mobility, mu, becomes a function of VGS. What's going on is that when we're making a transistor, really, why do we get short channel effects or so? Well, it's because the fields get very large. Well, there are really 2 fields. One of them is the field in the channel, right? That's VDS over L, on average at least, something like that, right? The other thing is the vertical field. And that sort of Tox over or VGS over Tox, right? And when that field gets very large, then it's sort of like driving across the Bay Bridge or Golden Gate Bridge, and there is a really hard wind. You're going to go slower, right? Because it's going to be hard to stay in the lane when you have a strong crosswind that tries to push you over the edge of the bridge. That's exactly what these electrons see here. They see a lot of side wind, and they slow down. Now, I'm sure a physicist would object to this kind of explanation, but that's sort of what's happening. And the key thing is that the electrons slow down, and so suddenly the current and mobility and so on depend on VGS. Well, that's not in the square law model, which assumes that mobility is a constant, and consequently you get the wrong results. Right? Okay, so really, totally regardless of channel lengths, for modern devices, or a simple square law model will not give accurate results, usually. Okay, I've already said that regions of operation and so on, of course, they're a little bit fake too, right? I mean, the device doesn't go, suddenly you apply the threshold voltage to it, it goes from one region of operation to something totally different and so on. That's also not physical. But the notion of these different kinds of like a linear region or saturation where the transistor can operate like a resistor, or it can operate more like a current source, that really is useful qualitative description, and we'll keep on using that. Okay, so one thing that is very important about the square law model is that really the square law model and these regions of operation, it involves two terminal voltages, right? A MOS transistor has three terminals, and so the voltage between any two terminals is known once we know the voltage between two of these three terminals. I mean, we know two of these voltage pairs. And so the voltage that we generally use to describe, you will need to reduce the zoom a little bit this time. So here is no way to zoom out. Okay, so no, the other way. Okay, good, thanks. So VGS is one voltage that we generally use, and VDS is the other one, right? And now, depending on how we choose VGS and VDS, we're going to be in one or the other box, right? In one or the other region of operation. Of course, it's also correlated because here the condition on which region we are in depends not just on VDS, but it also depends on VGS, right? We know those. So here there is probably nothing new in this entire chart for you, with the exception some may not have seen the equation for weak inversion. Some some simple. So these two equations, I'm sure you have seen this. You obviously have seen. Some simple descriptions of transistors. They say that if I make VGS smaller than the threshold voltage of the transistor, then the current immediately drops down to 0. That is approximately correct. It's not quite correct, and in this world of low power and so on, it's an opportunity to exploit that extra current. Also in digital designers, they have the problem that this is actually their leakage current, right? And so they know this too. So in this weak inversion region, when VGS is less than VTH, then the current. And now I would like to just have this here. Then the current is proportional to the exponential of VGS. And in fact, this equation here, forget about the W over L for a moment. This equation should ring a bell. You probably have seen this equation before, if not for the MOS transistor, then for the bipolar transistor. A bipolar transistor has exactly this kind of characteristics. IC equals some current IS times e to the VBE over VT. Right? So for small VGS, less than the threshold voltage, MOS transistors actually kind of behave like bipolar transistors. And that region is called weak inversion. And it is fairly important, so we include it here. This is a term when it also depends, the current of course also depends on VDS, but usually if VDS is relatively large compared to VT, then the transistor is in saturation, MOS saturation, and this term is really unity. Okay, and so again, I mean, transistors are reasonably described by these different regions of operation, but of course it's unphysical to think that the transistor is in strong inversion and then we change VGS by 1 microvolt and suddenly it's in weak inversion, behaves totally different, right? In reality there is some transition region. Actually it's hundreds of millivolts. We'll see that later. Okay. So so weak inversion, less zoom please. Weak inversion has, thank you, has actually two names, subthreshold conduction or weak inversion, same thing. Use either. It's just to confuse you. So it's kind of like the BJT. A BJT would have IC is equal to IS times the emitter area, right, times e to the VBE over VT, right? That's the BJT. The MOS has ID is equal to some kind of an IS times W on L times e to the VGS over Vt, and then there is one additional thing here, there is a factor n here. Right. And this n here is always larger than 1. What is this n? Well, actually, if we look again at our cross-section, I find those really handy. So let's say this was an n-channel transistor, so n plus, and in the middle here we have the channel. Well, our substrate, of course, is p-doped, right? So we really have here an n-p-n transistor. This thing really is like a bipolar transistor and looks something like this, right? And I arbitrarily assign the emitter to one of the two terminals. It's really symmetrical, unlike actual bipolar transistors that, due to the fabrication, actually come out asymmetrical. This bipolar transistor is actually totally symmetrical with respect to collector and emitter. Okay, so if we somehow had a means to control the voltage here in this space, right, then we would have really a bipolar transistor. Probably not a very good one, because in a good bipolar transistor, the width of the base is very, very small number, and here, well, it's not that small number, although this is the length of L, so whatever, right? Now, we don't really have control over the voltage here directly, because there is no terminal that goes to this thing here, but we sort of indirectly have control, because this is Vg, right? And somewhere down here, probably with another body contact, P plus, this is going to be Vs, right? So if we change the voltage here and we leave, let's say we ground this thing, so of course the voltage here is going to change somehow. But we don't contact ohmically to this thing, the channel here, but we contact capacitively. We have here a capacitor, and then here actually we have another capacitor, C channel bulk. Because this is a semiconductor, as we change the potential here, more or fewer carriers go into this region, into the channel region of our MOS transistor that acts sort of like a bipolar transistor. Right? So we actually can modulate the number of carriers that we have in the base of these transistors by modulating or by varying the voltage on the gate of the device. Now, of course, there ought to be a penalty for not just setting the potential of the base, but goes through this capacitive connection. And in fact, we ought to have capacitive division between this capacitor and this capacitor to this voltage here. That is really the base voltage. Right? Well, this factor n is precisely the ratio of this capacitive divider. And the actual value, of course, varies depending on the doping and the oxide thickness and so on, so it's technology dependent, but typically it's around 1.5. Okay? And for our process also happens to be about 1.5. So that's why we get this factor of n. Is it a good thing? Well, not really. I mean, what I want in a good amplifier is that for very little input, for very little control, I get a lot of SIP. I get a lot of output. Right? If I have a sports car, I depress the accelerator just a tad bit, and this thing flies off. Right? Same thing with the transistor. I wanted just a little bit of VGS change, and a torrent of current comes out the other end of the thing. That's what I want, right? So this exponential, heck, I mean, that's a great thing. That's about the right function, right? Of all these functions, super exponential would even be better. Don't know how to do that. So exponential is good. Now this factor here should be very small. I don't want to cut down my control signal by a whole lot. So this n business, it's a bad deal, but you know, you have to live with it, right? Okay. Now exponentials, of course, are better than squares if I want to get a lot of output for little input. So weak inversion, heck, it looks pretty attractive, right? Not quite like a bipolar, but almost. there is a downside to it, and we will talk about that, and that is that it's relatively slow. Why is it slow? Well, because in order to make VGS very small, suppose that I want to run a certain amount of current, let's say 100 microamp, and we'll see why I might want to actually run 100 microamps, right? Then I need a big transistor to keep VGS low. Well, a big transistor means that I have a huge CGS. A huge CGS means that there is a capacitor somewhere in my circuit that's going to slow things down. So there's going to be a trade-off, and we're going to study this trade-off. But this moderate or weak inversion is becoming ever more important. And there are really two reasons. One of them is obviously that's where little current flows, so it's got to be low power. And the other thing is that as we make our devices smaller, for increasingly less current, we can go faster. And so invariably, we need only a few microamps to run our amplifier at 100 megahertz. Well, and then the device is in weak inversion, right? So when I took the equivalent of this course, well, unless you wanted to go at kilohertz speed, weak inversion wasn't for you. Well, now often we run a device at 100 megahertz, and it's almost in weak inversion. There is a disadvantage that is not specific to weak inversion, but to this exponential law. So we got to be a little bit careful, and that is that suppose we wanted to build a mirror, something like this, right? Okay. And now, let's say that these two devices, they ought to have the same threshold voltage, but they don't quite have the same threshold, right? There is some delta VTH, right? Should be 0, but it's not. So this device computes the right VGS to run whatever IREF we stick into it, right? So then this device over here goes and takes this voltage, amplifies it exponentially, and runs the output current. Well, if in an exponential we have a little bit of a delta VGS, even if it's small, we get a huge error. In fact, delta VGS of 60 millivolts is a little bit on the steep side, but in a bipolar transistor, it takes just 60 millivolts to change the collector current by a factor of 10. In this MOS device, we have this other factor of n in there, so instead of 60 millivolts, we need n times 60 volts, or 90 millivolts to change the current here by a factor of 10. Okay, we're not going to have a threshold mismatch of 90 millivolts here, right? That would be a little bit extreme. But we also don't want to have an error here of a factor of 10 in current, right? So it's very sensitive. In fact, in bipolar devices, it's not quite as bad because VBE mismatch is smaller than VTH mismatch. But even in bipolars, they put resistors in here. Now, we could do this resistor business also with MOS. Would you do this? What would you do rather? Yeah, specifically, what do you make bigger? Yeah, you make L bigger. That brings the device out of weak inversion and increases VGS, and we don't have the problem anymore. We are not nearly as sensitive. Reduces GM. Which is probably okay if this is just for biasing. We don't need speed. If this was to actually run the signal through, well, then it might not be such maybe a compromise. Okay, so nothing is totally for free, but you can be a little bit careful. But we can exploit this, and so often what we will do is we make VGS very small in a diff pair to get reasonably close to weak inversion, and so have CP transistors, right? And in our current mirrors or so, well, we make L big so that we are far from weak inversion. Okay, so So now, that was about sort of the generalized or extended square law model, right? Now we have to talk about why we can't use that model. And there is a long list of reasons, and I list a few of them here. But I sort of summarize them as short channel effects, even though some of them are really small width effects with thin gate oxide effects or whatnot, right? Or high doping effects, what do I know? There are a couple of the more significant effects I'm listing here. One of them is that the threshold voltage becomes a function of device dimension. Turns out that if you make L small, the threshold voltage goes down, and if you make W small, the threshold voltage goes up, and bizarre stuff like that, right? So that's one thing. And the other thing is mobility reduction. I've already mentioned this business with the vertical field, right? That if you have a thin gate oxide, a large VGS, well, large, I mean a volt or so, then the mobility suddenly drops, right? Because of VGS. As we increase VGS, the mobility gets smaller. And then there is this velocity saturation. That's probably the most widely known issue here, and that's the field in the channel, a lateral field in the channel, and it's just heck if VDS is a volt or so, and you put these things closer and closer together, the field here gets bigger and bigger, and then what we really have is the carrier velocity as a function of electrical field looks something like this, where this slope here is precisely the mobility, but as we increase the field, we reach a value that is usually referred to as the critical field, and then the velocity of the carriers doesn't increase any further. So this whole concept of mobility, I guess, is a little bit of a crutch, because it's reasonable down here, there is really a proportional relationship between velocity and electrical field, but for a higher electrical field, that's just plain not true. And I guess I just got a break when I went to school that we safely always operated down here and it didn't matter. And well, you now are facing the whole thing, and so you got to worry about this part. All right. So the net effect, of course, is that we end up with less ID than we think that we should have. Okay, let's look at these things just a little bit. Okay, so here is the threshold voltage. If you can zoom in a little bit just to this area, thank you. Here is. So all modern versions of SPICE, they have a way that you can ask not just what is the current that's flowing through my transistor, but you can also actually ask it what it calculated internally as what the threshold voltage was, or the transconductances of the device. I use that liberally, and I suggest you do also, because then you can know all these things, right? But you have to look up in the HSPICE and Spectre and so on, all these different versions of SPICE, they use a slightly different way on how to do that. So you have to look it up in the manual. But then it's very handy. I also, in all these slides where I show and go and look at I mean, extract from SPICE threshold voltages. So I show the circuit how I do that. So they're usually very simple, but sometimes require some thinking, like when we looked at capacitance, right? So here is plotted now the threshold voltage as a function of channel lengths. So here is 0.35 micron minimum channel length, and we can see, for example, for the NMOS transistor, well, this is the nominal one. It's about 560 millivolts, the threshold voltage. But then if we were to use a 1 micron device, so this is like 560 millivolts, 1 micron device suddenly it would be 800 millivolts. So really significant. I mean, makes a huge difference. And the funny thing is that the PMOS device behaves completely different. In fact, the PMOS device, so that's the opposite, right? And that's a further complication, right? Sort of this idea that the threshold voltage should drop as the channel lengths get smaller. That comes out of textbook calculation. It turns out it's not that difficult to calculate or show in it, but that depends on textbook calculations, textbook examples. And they, of course, assume that you have uniform doping in the entire channel. Well, if you don't, then things can be quite different. And so manufacturers, they exploit that they use complicated or clever doping profiles that sort of to first order correct the variations of threshold voltage. I guess this was the PMOS actually I showed here, and these two, they are NMOS. Anyways, key point is that the threshold voltage is sort of a strange, an inconvenient parameter, varies all over the place and so on. But fortunately, threshold voltage isn't all that important in most of our circuits. For example, if we look at this current mirror here, the problem wasn't that these devices had a threshold voltage and what the value was of that threshold voltage. The problem was that they didn't have the same threshold voltage. So most of the time we use like a current mirror or a diff pair or so, and then the absolute value of the threshold voltage isn't that important as long as it's not larger than the supply or a substantial fraction of the supply. So it's inconvenient, right? It's just got to be equal. So how do we make it equal? Well, we make devices that are certainly both the same length and they're close together. But there is one more thing. Imagine that we chose, and now I need more zoom again. Imagine that I made a device that had, let's say, half a micron channel length here. Well, the channel length also varies a little bit, right? Depends on this $1 million lithography tool and probably a few other things. Anyway, it's going to stray a little bit. Well, if it strays a little bit for this device, it's just a tad bit higher. My threshold voltage changed by a whole lot, or a tad bit lower. Get totally different threshold voltage. So for given lithography capabilities, I would expect my half micron device to show pretty significant threshold voltage variations. Well, yeah, it does, right? So if I want to have, if I depend on good threshold voltage matching, I got to use a 1 micron device or 1.5 micron device. Now a little variation doesn't result in a significant change in threshold voltage. Okay. All right, I list some of the things here. This part here is just backgate bias. Right, this body effect, and that you probably have seen already also in these equations. So if any of that looks unfamiliar, so go back to your undergraduate text and look it up. And if you can't find it, come see me at the end of class or during office hours or get the questions answered. Right? Sometimes we need this. Run-to-run variations of threshold voltage. Right? Threshold voltage target value for 1 micron device, 600 millivolts. Well, as you get runs, they will be sort of distributed over 550 to 650 millivolts. For another process, of course, the distribution may be broader or narrower. Device-to-device matching, if the devices are close together, so maybe is a lot better. And again, it depends on channel length. So for reasonably long channel lengths, a micron or so, then the variation is maybe a sort of a 1-2 millivolts or so. Now, generally, that's described with the standard deviation. And what does that mean? Well, it means that if we make a bunch of devices, so here we have, you need a little less zoom. Thanks. So here we have the target threshold voltage, right? That's the threshold voltage that all of our devices should be getting. Now, most of our we forget about the systematicness, most of our devices are going to have, so this is the number of devices that have a particular value of threshold. Most of our devices will be just dead on. Some of them have a little bit higher, some of them a little bit lower. Sigma is the width of this curve. In fact, this is sigma, and this is also sigma. So this would be VTH minus 2 millivolts, and this over here would be VTH plus 2 millivolts. Right? So really, if I say that the offset of my device, the threshold voltage offset of my device is plus minus 2 millivolts, what I mean is that my device falls into this region here. Well, but it turns out it's only about 70% of all devices that fall into plus minus 1 sigma. So in practice, typically we will use plus minus 3 sigma, so 6 millivolts plus 6 millivolts, and then the number of devices that fall between these two loser bounds, plus minus 3 sigma or 6 millivolts, is going to be 99.3%, something like that. So now it gets sort of more reasonable. Then we actually have a chance to make a bunch of IC that a fair number of them actually meet our constraint. We've got to be a little bit careful when manufacturers or whoever quotes these sigma numbers. Well, the offset variation of our device is not 2 millivolts. It's sort of a majority of the devices is within there, but we'll need to multiply this by 3 to get really a good majority of our devices in there. All right, so now, before we get into too complicated equations, so let's ask ourselves the question: once we are through with this device modeling business and so on, what do we really want to know? What are really the right questions to ask, right? So that could save us a lot of time of answering questions that we really didn't need to ask in the first place. Okay, so first of all, most of the time it turns out we're going to use our devices in saturation. In other words, VDS is much larger or large compared to what's usually called VDSat, VGS minus VTH, right? Then our devices operate like current sources, and it turns out that's really the only region of operation where you can make a decent amplifier. Otherwise, you can make some kind of a resistor, but not really an amplifier. And the other thing is we're going to work in either moderate or strong inversion, not really deep weak inversion. You use a little bit of weak inversion maybe, but not so. And the other thing is, what are really the key parameters? What do we really care about when we design things? Well, at the large signal level, if you just can zoom into this region. Thank you. So at the large signal level, we certainly care about current, right? Incredibly important. It's got to be 0 all the time. Well, we might not be getting there always, right? So 1 microamp, but current's important. A model that doesn't say anything about current is going to be useless. Okay? The other thing that's very important is minimum VDS, right? We said that we want to operate in saturation. That means that our VDS needs to be a certain number, right? A few hundred millivolts or something like that, right? Very important. Hey, heck, our supply voltage in 240, maybe it's 3 volts. In reality, it's 1 volt, right? Increasingly. So another 100 millivolts more or less, heck, I mean, that breaks the bank, right? So a model that doesn't say anything about this minimum VDS, useless. Those two things we need to have. Transconductance. Well, most of the time, why do we use transistors? Well, we want to make amplifiers. GM is the gain. That's the currency of how good our amplifier is. That should be infinite. Okay? And it determines, lastly, how much voltage gain can we get, and even more importantly, how much speed we can get out of this thing. If GM is infinite, we can build infinitely fast circuits. So we want to know something about GM. We want to know about capacitances. If these transistors have huge GM, but they have even huger capacitances, like drain to bulk capacitance of 10 picofarads or God knows what, right? That's a problem. So we want to know something about the capacitors too. And we want to know a little bit something about the output impedance, because if we don't have an output impedance that is much higher than 1 over Gm, we can't get voltage gain, right? So these are really the things that we want to know about. If we don't have information about these, we can do analog design. Okay. So well, of course, one thing that we also use very liberally in analog circuit design is the analog circuit small signal model, and I show it here for DC. So there are really two parts to it. One of them is that I want to have gain, and because the output of my thing is really a current ID across, right, this is drain, source, gate. Okay, so and the input is VGS. So my gain is really something that has unit transconductance because it goes from a voltage input to a current output. So my transconductance Gm is equal to D out, what is comes at the output, DID, right? D VGS, right? And so that is Gm. So that's how we get to this Gm. The only reason I put this here in this clumsy way is that sometimes people get so worked up with their cheat sheets and writing down all these 3 different equations for transconductance so that they forget that transconductance is nothing somehow God-given. It's just, this is the definition, right? We can calculate all these equations trivially. Right? That's really what transconductance is, just differential of output with respect to input. Okay, and the other thing is that also matters at in the DC model is that we have, as we change VDS, the current changes also a little bit, unfortunately, and that's our out, and that also is given by a simple equation. Here, if I change the voltage, the current shouldn't change, but it does, so dVDS, dID, or 1 over that. Probably a better way to write that would be 1 over R out is dID dVGS, because then you could, for example, use the square law model to calculate what R out is. Otherwise, you would have to solve first for VDS. You still have to solve for VDS and just off it. Okay. All right, so let's go and look at this transconductance. Well, we have now 2 regions of operation, weak inversion, strong inversion. Of course, in practice, we're going to be somewhere in between them. And even though there are models that give us equations for what's happening in between there, we're not going to put up with them because they're just too complicated. Right? So I use now this equation for calculating Gm, and I found that Gm for my weak inversion transistor is really ID over Vt, and this little factor 1 over n here, that's really exactly like a bipolar transistor in a BJT. It would be IC over Vt, right? That's the BJT. Okay. So the transconductor is really proportional to the amount of current that I stick into my device, and then it's also cut down by Vt. Okay. Now, if I go to strong inversion, I assume for a moment that we had this square law model. Then I get this expression here. Incidentally, it looks very, very similar to the bipolar device or to weak inversion. Again, we are proportional to ID. But if you want, the proportionality constant isn't so good anymore. Well, the factor of 2, of course, is nice. Wonderful. But VGS minus VTH usually is a lot larger than VT. Right? And that is also something that we got to be very careful. So that is sort of opportunistic and mathematical thinking is, heck, I mean, why not? Let me make VGS minus VTH 1 millivolt. Then I'd, well, VT is 25, right? then I do a lot better than a bipolar transistor. So why isn't a MOS better than a bipolar? Why isn't that going to... did we just invent something great? Revolutionized the world. They always thought that bipolars had more transconductance, but this equation says just got to make VGS minus VTH small enough, and then I beat bipolar by a long shot. Why doesn't that work? Well, it does. It's very simple. Strong inversion is a contract. And the contract of strong inversion is that VGS is much larger than VTH. Okay, so this must be much larger than 0, or much larger than VT for that matter, actually. And consequently here I'm always worse off than over here. That's why. Okay. I saw this once in an undergraduate circuits course where they used SPICE level 1 models, and SPICE level 1 models they exactly use this equation, and they had to sort of build the best amplifier, some strange constraints, and it was really possible to make this VGS minus VTH a microvolt, and get something out of SPICE that was just phenomenal. Of course, you can never build it. Right? Okay, so let's look at the transconductance now invoking SPICE. So our equations predict that transconductance is proportional to ID. Okay, here actually what I'm drawing is, I'm drawing the transconductance as a function of VGS. Okay. And I tie the drain and the source of my transistor, I tie them together. That way my device is always in saturation. Okay. So then, if we vary VGS, of course, there is somewhere in between here, there is the threshold voltage, and I'm going from first weak inversion to moderate inversion to ultimately strong inversion, right? So I actually changed my region of operation. Now, if you rework these equations on the previous page a little bit, then the transconductance in weak inversion actually increases exponentially, at least theoretically exponentially, with VGS. And so I plot this thing on a log scale, and lo and behold, I mean, on this log scale, the exponential then turns into about a straight line, right? And so where this is about a straight line, my device actually behaves the way it's supposed to behave in weak inversion. There's a fairly large region where it does. Right? And then somewhere here where it starts deviating, I enter moderate inversion, right, or transition region. Okay. Then for values of VGS that are larger than VTH, my transconductance should increase proportional to VGS, so that would be this line here. But in reality, it bends over quite significantly, and the reason here is these short channel effects like velocity saturation, also vertical field, and so on. This sure looks fairly bad, right? I mean, probably somewhere around here I've lost a factor of 2 on my transconductance. But on the other hand, if we go down here, well, actually, maybe even a little bit different. Here is maybe the factor of 2 points. If I go down here, this has happened at about 1.6 volts, right? Well, how often are we going to have 1.6 volts across the VGS of our transistor? Well, so really, we're probably going to use our transistors most of the time somewhere here. And so the deviation is significant, but it's not a factor of 2. But it's too big, so we're not going to use the square law model. Okay, so transconductance. From your undergraduate courses, you're probably used to a wonderful sheet that your instructor gives you, and it lists a bunch of numbers, and one of them is mu Cox, and you use this mu Cox then liberally in your equation and calculate all the interesting stuff, right? Well, here we can do the opposite, right? We can actually, for a square law device, we can calculate what mu Cox is, just 1/2 W, right? We can solve for mu Cox, and we can plot it as a function of whatever we like, and in this case, I actually plot it as a function of ID. So this is by simulation that shows the value of the effective value of mu Cox as a function of ID. Even if we sort of forget about these very small IDs that correspond to weak inversion, then we see that there is quite a variation. It depends on the channel length, it depends on the ID of the transistor, and so suddenly there's sort of 10% variation. So if you don't want to get very accurate, then well, maybe for our process you can use mu Cox for the NMOS of about 150 microamps per volt square, right? Yeah, and for the PMOS maybe 50 or so, but it's not going to be very accurate. Right? So really the only reason why I have this slide in here is that this safety anchor of mu Cox is a bad safety anchor. It doesn't hold. You drift off with that thing, so we don't use it. Okay? So we've seen it now. Why? And let's forget it. Never ask me again, what is mu Cox? Well, this is what it is. Varies all over the place. Can't use it for design. Yeah.
These effects include velocity saturation.
Oh yeah, this includes everything, because really, I mean, I haven't done a measurement. I use here SPICE as a sort of, I assume that SPICE has actually absorbed the real behavior of the device, and so instead of running a real measurement, I just run SPICE to effectively measure. Oh yeah, it includes everything. Okay, now we finally get to something that's really interesting. And that's the efficiency of the transistor. We've said before, what we really want from this guy, from this transistor, is GM. There should be infinite, right? And what we don't want is power dissipation. ID should be 0. So a good device will have a good efficiency, GM over ID, that is infinite, right? So this is really what we want from our device. So this is a good figure of merit. If you can give me a device that has higher GM over ID, thank you very much, I'm going to use it, right? And so I'm plotting this GM over ID as a function of VGS. And I also, again, I made VGS and VDS equal, so that it's always in saturation. So this is VGS. And then this is GM over ID here. Okay? And, well, about here I have sort of 500 millivolts. That's about my threshold voltage. So what region of operation am I in here? And what here? Well, this is weak, and this is strong inversion. Right? So, if I want efficiency, and well, who doesn't want efficiency? I want to be here, somewhere here, right? So now we also sort of can understand it. Why? If we can afford it, we're going to run our devices kind of close to weak inversion or even in weak inversion. Now, of course, there's got to be a penalty, right, to running them way down in weak inversion. We've seen already. CGS gets a little bit large, and we'll capture that also in a slightly improved graph over this. But to a good extent, it's good to make VGS small. It's good to get close to weak inversion if we want high efficiency. And generally, we want that. Notice also that once we really have made VGS fairly small, let's sort of put it that way, making VGS sort of a volt and larger is really costly, right? The efficiency now is way down. But on the other hand, once we've made VGS sort of in the 600 millivolts or so, then, yeah, we win still a little bit, but it's not that big a deal. So really, that's probably an interesting region of operation if we have some compromise, if we cannot just operate over here. Okay, notice also that for a BJT, GM over ID, well, for a BJT, GM is equal to IC over VT, and therefore GM over IC is equal to 1 over VT, or that is 40 times 1 over volts. The units of these things are really a little bit strange, 1 over volts, and we get to this. The efficiency is a good idea, but the unit is really not very good. So, but that just so happens, right? Figure of merits, they have whatever unit they like. So a bipolar, this number here is actually 28. So a bipolar would be up here, which would be just 50% larger about, right? Because N is 1.5 than the MOSFET. So a BJT for well, there is no really VGS, right? There is a VBE. A BJT is always up here in efficiency. Okay, that's why we like these guys, these BJTs, right? Then they have, unfortunately, a few other characteristics that we don't like so much, so that we don't use them nearly as much anymore. But that's what's going on. Okay, so now efficiency is really important. We're going to use this over and over in our design, and we're going to, very often, I mean, sort of one of the key design decisions is what efficiency are we going to have on our transistor set. And there's going to be lots of issues. Obviously, there is a price for running at high efficiency. Otherwise, I wouldn't be going through this thing. So I've already mentioned the unit of 1 over volts is really inconvenient. So instead of using GM over ID, I define a new quantity. If you can zoom into just the red box, please. Okay. I define a new quantity, 2ID over GM, and I call this quantity V star. Okay? And then this V star happens to have a unit of volts, so that's convenient. So that's it's a good step in the right direction. And of course, once I know V star, I easily can calculate what is GM over ID. So for example, if I set this V star to 200 millivolts, for God knows what reason, that would correspond to a GM over ID of 1 over volts. So I would be, well, just here on my graph. But I've messed up now completely, right? So fine. So, well, if he likes V star, we can put up with it. Now, there is something that is both good and can be very confusing, so be careful about that. If, and only if, and consequently never in practice, we have a square law device, then V star happens to be just equal to VD set, or VGS minus VTH. But that's true only for square law devices. Now, if we had a square law device, and this, I repeat, if, this if is a condition that never happens, but if it happened anyways, then, of course, this VD set, which is equal to V star, would also just tell us the boundary where we go from triode region into saturation. So, in other words, it's about the voltage that we need. It's about V star is approximately equal to VDS min, right? It's only approximately true for two reasons. One of them, even a square law device, right? This idea that the device turns from, is really a resistor into a current source, just at one precise voltage is a little bit hypothetical, right? I mean, physics doesn't work like that, right? There is some transition. So that's one thing. The other thing is, we don't have a square law device, and consequently, V star is not equal to VD set. But nevertheless, V star is going to be a very, very good indicator for how much VDS we want to have across our devices. So in fact, sort of reasonable rule of thumb is that if we have only V star across the VDS of our device, the gain is, or out and constantly gain is really going to be low, and if we have about 50% more, then we get decent gain. If we have 2x more, then we have really good gain, but we've used up a lot of voltage headroom. We're going to talk about that, but point is that V star now suddenly becomes a very, very interesting number. One of them is it tells us how much VDS we need. It's important, right? And the other thing is it tells us something about the efficiency. We want to make V star fairly small. In fact, as small as we can, because the smaller we make V star, the higher the efficiency of our transistor, at least until V star was made. I mean, until we get sort of to a couple of VTs, right? But if we get below 100 millivolts or so, then the efficiency really doesn't increase anymore because we are in this flat spot here, right? So in practice, we're gonna generally design our transistor for V stars from, well, about 100 millivolts at the really low end to more typically 120, 140, 150 millivolts. Really, we're going to shave off millivolts there. We're going to be stingy on that one. And then 250 millivolts is really kind of very large. We will do that occasionally, and there are sometimes very good reasons to do that too. Okay, so now we've got something really important. This V, of course, V star. You can call it VD set if you prefer, right? But the trouble is, if you call it VD set, then you don't have this automatic reminder that it's not really VD set because we don't have a square law device. That's why I invented this V star. You won't find it in any textbook or anything, but I just found that I constantly had a total mess, all sorts of confused people, and I said, well, I can invent a new symbol and fix this problem. Okay, so let's go on now. So far, we've looked really at DC stuff, right? Current, how much voltage do we need, transconductance, right? Those are all DC parameters. Now, to get a full picture, we need to, of course, look at the AC part because we want to get things fast. Right? And so for that, we extend now our small signal model to also AC, right? So first of all, we have here the CGS. We have from the source to the substrate, we have a CSB. From the drain to the substrate, we have a CDB. Right? And then we have also from the gate. From the gate to the drain, we have a CGD. So these are all things that you've seen this 100 million times. I just put this here to remind you or put you asleep, whatever. Take your favorite. But in case this puts you asleep, then I have a question for you to maybe. What about CSD? Right? I mean, after all, we have here 4 terminals. There ought to be a capacitor between any 2 terminals, right? Any pair of terminals. So, why is CSD missing? Or, in other words, what's the value of CSD? Remember your undergraduate textbook? What does your undergraduate textbook say about it?
Overlap capacitance from the
source and the drain. Yeah, right. So I can tell you, your undergrad, you can try to remember as much as you want. Your undergraduate textbook just says nothing about it, nothing. And of course, if you look at the transistor, right, then we have a source and a drain, and yeah, they don't overlap, and so the capacitance between them ought to be pretty small. And if we lay out the transistor right and so on, lo and behold, it is. Be very, very careful because then you wire up this device and you build a nice little bridge and crossing here, right? then it's no longer 0. Well, it depends on the circuit, but I can tell you in some circuits it's really a pain if you have a large CSD. So be careful, right? Yes, it's true that normally this CSD is completely negligible and you don't need to care about it, but you certainly can mess it up, and then sometimes it's not so funny. Okay. Now, I've mentioned before that PMOS transistors in our process, because they have are really 5-terminal devices. So it's everything what we had, but there is one additional thing, and that's this this diode, right, between the well and the substrate. And so we have an additional capacitance here. And the rest is the same as we just had before, but there is this additional capacitor C bulk substrate, and if you want to put it in, if it matters in your circuit, and sometimes it matters, cuts down the common mode rejection at higher frequency of diff amps and stuff like that, then you need to specifically stick it in. You need to figure out how big is this thing and hack it into SPICE. For that, in the models that I've posted on the web, there is actually a diode that's called a diode called D-Well, and you can stick that in. Likewise, of course, you can if you actually want to forward bias this diode, and I can assure you that the circuit's not going to work very well if you do that. Okay. Then this here is something that where your undergraduate textbook says a lot about. That is, how do we calculate the capacitance between any of these two terminals. Now, there are just a couple of points that I want to mention. So first of all, CGS is, when we are in saturation, is going to be 2/3 CG plus the overlap capacitance, right? So there's 2/3 and so on. You've seen that. One thing that I want to mention is this overlap capacitance. In undergraduate courses, you generally use this LD parameter to calculate the overlap capacitance. It doesn't work very well. So what does work fairly well is, and generally they actually specify, but then you build a little SPICE circuit to figure out what is the overlap capacitance per unit length, or per unit width actually of the transistor. Right. So I extracted these numbers for our process, running actually just SPICE, and it's about 0.24 femtofarads per micron. So if you have a transistor with width 100 micron and it's an N channel, then the overlap capacitance is going to be 100 times 0.24, 24 femtofarads. The overlap I get. For the PMOS, happens to be just twice as large. In another process, of course, it wouldn't be twice, it would be something. But they are not always the same. Right? So that's how we calculate the overlap capacitance. The other thing that is often not included in many undergraduate texts is that the capacitance between the channel and the bulk, right? The thing is that, of course, the transistor has a sort of the 3 terminals, source, drain, and gate. We are interested in those, but really, charge is stored in the channel, and so there really ought to be a capacitance for that channel, and that is even a distributed capacitance and so on. And so this channel to bulk capacitance really takes care of that. I go over a complete example where I calculate this for a device and get reasonable numbers, and then run SPICE to compare. I'll let you go over this. I don't want to spend a lot of time on this. You can simulate this also. If you can use more Zoom just on the. Thank you. So here is, for example, the CGS, and here I vary again VGS, and I made it that here I run into saturation. So here really I get 2/3 of I get this 2/3 2/3 of WLC ox and so on. So you can verify this. Okay. One important thing is layout. And that is, depending on how we lay out our devices, we can actually, well, first of all, we also get, in addition to these so-called intrinsic capacitance of devices, so that's the CGS, it's essentially the CGS side. We also get the extrinsic capacitance, that's the capacitance associated with the isolation diodes, source to bulk and drain to bulk and so on. They kind of, we get them for every device, but they're not fundamental to the device in the sense that if one of you has a brilliant idea and figures out a way to how to get rid of these capacitance, we would have a device that doesn't have a CDB, and that of course would be a great advantage, and SOI is kind of trying to do that, right? With CGS, the story is a little bit different. If you figure out a way on how to get rid of CGS, well, you probably have gotten rid of the transistor, right? So it's really intrinsic to the operation of a MOSFET that, of course, you have a gate capacitance. All right. So the intrinsic, the CGS, we really can't do a whole lot about unless we don't want to give up on the transistor in the first place. But the other capacitance, the extrinsic ones, there we can do something about. And in particular, the source to bulk and drain to bulk capacitance, we have some handle over, and an example is shown here. Suppose that we actually want to build a common source stage. Then the CSB is just in parallel. It's just shorted out, right? So we really don't care about the value of CSB in this configuration, at least. It would be different in a cascode. Here we have the CDB. Well, that just loads the output of our stage, right? I mean, we built this big amplifier, but now it puts its own load capacitance there to slow itself down. Well, that's not a big deal. So that's not a good deal, right? So we really want to make this guy small. Okay. So well, let's look at different layout choices. Here, let's say that we needed a device that had a certain width W and a certain also given length, maybe a 100 micron wide and 1 micron long. Well, we could lay it out like that, and then we get, of course, source and drain capacitance. That's W times whatever this thing is. In our process, the minimum is 1 micron, right? We could have laid out this device also as two devices that then we wire in parallel. We just wire their gates together and their sources and their drains together, right? Then we get something like that. Now we can share one of the two terminals. This terminal we can call whatever we like to. Here I would like to call it the drain terminal because obviously this thing has less capacitance than these two junctions together, right? So now I found a way and put the numbers here to actually reduce the amount of capacitance by more than a factor of 2. Why is it more than a factor of 2? Well, the area between this thing and this thing was cut down by a factor of 2, but the perimeter was cut down by a lot more. Here I have perimeter W plus 1 micron plus 1 micron, and here I have 1 micron plus 1 micron, 2 micron. Right? So the perimeter was cut down very significantly. And so this layout really helps. So how do we specify that? Well, we don't really, usually we don't draw something complicated like that in our schematic diagram, but we need to tell the layout guy, heck, use a finger transistor, right? And this is how many fingers you're going to use. So what we do is we would write down W over 2, I mean the dimensions of just one finger, right? And then we would also write next to it that we want to have 2 of these in parallel. And this nomenclature actually is even supported by SPICE. SPICE understands that if you just use, in addition to W and L, you use also M as an additional parameter does the right thing. Now, one word of caution is that unless you have SPICE set up correctly and the right version of SPICE, then SPICE is very optimistic and very generous. It makes the area and the perimeter for these junctions 0, and consequently you don't get any loading, right? I mean, it's really neat, and I like it, but you know, it of course isn't exactly reality, and so then ultimately I get the bill for this. So be very careful. It does take time, but you need to specify what AS, AD, PS, and PD are. Right. And if you don't do it, then you're fooling yourselves. Now, in HSPICE, there is a way to set this up so that it automatically calculates reasonable values. That may not be even too far off. In other versions of SPICE, like Spectre, you can make macros which take W and L and then calculate the right AS and so on from those, in addition to W and L you've specified. Okay. What is this? More example, right? There is one more thing that is important that I wanted to mention, and that is that our entire model of how to deal with device capacitances is really fundamentally flawed. And the reason is that this is sort of our thinking of the device, right? We have really 3 terminals that we care about, and that we kind of know the voltage. We know the voltage on these terminals, or we could measure them with a voltmeter or so. So we really know about these terminals. So it's only natural that then we also say, heck, I mean, we want to model these devices by capacitors that are between these nodes. Well, that unfortunately just doesn't work. Well, why do we use a capacitor in the first place? What does the capacitor really model? Well, it models charges that are stored somewhere, right? And it models then the relationship between the amount of charge we have and the amount of voltage that we have somewhere also, right? Well, where is charge stored actually in our transistor? Well, most of the charge is somewhere stored here in the channel and the junctions next to the channel and so on, right? So really the right question to ask is, what is D, Q, what is the change of the charge that appears at the source associated with the source terminal as a function of changing VGS, or changing VES, or changing VSB, or whatnot, right? And then I can of course call these different capacitors. I can call these now capacitors. I could say that this was CS, GS, or CS, DS, and so on, right? I really define now a whole matrix of there are 3 terminals, and there are consequently actually 2 such voltages here. I also added the bulk terminal as another one, right? So then I have 4 terminals. So I get 4 such charges, and I get of which 3 are independent, right? The total charge in our device better sums to 0, and I also get 4 voltages between all the terminals, bulk terminal and the 3 other ones, of which 3 are independent. And then so consequently I have a matrix of 3 by 3 or 9 such derivatives. And SPICE actually does that. SPICE actually calculates those 9 derivatives. And then you sort of can say that, well, I mean, the charge at the gate, its derivative with respect to CGS is about equal to CGS, so I want to call this CGS. Yes, you can do that, right? And then you map to these capacitors that we have. But it's really not accurate. And if we stick with this model of these sort of modeling capacitors like CGS, so instead of really taking care of the charges, then we run into a big problem. And the big problem is that SPICE internally ends up inventing or destroying charge. Now, since the 80s, when we started doing all these switch capacitor charge sampling and circuits and so, that became just a total nightmare. I remember when I did my PhD thesis, I ripped my hair out because it was a switch capacitor circuit, but SPICE wasn't up to the task yet, and I mean, the results were just totally non-physical that came out of the thing. So all modern versions, all modern SPICE models and so on, they use these charges. They model the charges, and then if you want to get a capacitance, well, it calculates these derivatives for you, but you really get 9 per transistor. And none of the 9 really corresponds directly to a simple but unfortunately flawed model. So you always got to be a little bit careful about these capacitors. Okay, so I guess we're still not totally quite there with designing a simple common source stage, but we'll get there.
So for this kind of parameters, for parameter for SPICE,